Welcome to NGVEX Explainer.
Hello everyone and welcome to the Explainer. I am so excited to jump into this with you today. We are taking a deep dive into a really advanced manufacturing technology that's, quite frankly, completely reshaping how we build the physical world around us. We're talking about metal 3D printing. It's this incredibly modern industrial process that takes digital designs and turns them directly into highly complex metal parts. Over the next few minutes, we're going to explore the specific materials they use, the really fascinating mechanics of how the process actually works, and exactly where this cutting-edge tech is being deployed out in the real world. Okay, let's dive into this. Here is our roadmap for today. We'll start with what metal 3D printing actually is, then how the process works, and the essential materials involved. After that, we'll look at the additive advantage, the real-world limitations and true costs, and finally, some actual industrial applications. Now, before we get into the how of all this, we really need to understand the why. Why is the industry investing so heavily in this? Well, look at this staggering statistic. In commercial aviation, reducing an aircraft's structural weight by just 100 pounds saves roughly 14,000 gallons of fuel per year. That is massive. Every single ounce matters. And as you'll see, metal 3D printing is the ultimate tool for stripping away unnecessary weight without sacrificing even a fraction of structural strength. So, Section 1, what exactly is metal 3D printing? What we're looking at here is a fundamental shift away from traditional subtractive manufacturing, like CNC machining, where you start with a big block of metal and just carve it away. Metal 3D printing is an additive manufacturing process. Instead of cutting material away or building it up, using metal powder or wire, the object is constructed layer by layer directly from a digital model. This means material is added exclusively where it is mathematically needed. By eliminating that subtractive waste, we aren't just saving expensive metal. We are opening the door to geometric shapes that literally cannot be milled or cast. And what's really interesting about this is that the whole entire process begins right here, at the microscopic level. Whether you're building a tiny medical implant or a massive rocket engine, the foundation is this highly pure, precisely sieved metal powder. It has to be perfect. If these microscopic particles aren't perfectly uniform, or if there's even a tiny bit of chemical contamination, the final part is just going to fail. Moving on to Section 2, how the process actually works. This digital-to-physical journey follows a super strict sequence. First, obviously, you create a CAD model and convert it into an STL file. Then, that digital model gets sliced into thousands of impossibly thin layers. And this is cool. Modern AI-driven design for manufacturability engines can now analyze these CAD files in just seconds to prevent thermal deformation before the printing even starts. Step 3 is the printing itself, where a laser or electron beam melts the metal powder layer by layer. And finally, Step 4 is post-processing, which is a rigorous cycle of cleaning, heat treating to relieve stress, and surface finishing. So here is Step 3 in action. This is selective laser melting, or SLM. A high-powered laser is selectively irradiating the powder bed, completely melting the metal into a fully liquid state. This is what creates that beautifully solid monolithic grain structure. But there's a catch. If the extreme thermal fluctuation during this process isn't managed perfectly, it causes severe residual stress, warping, and even microscopic porosity hidden inside the metal. All right, Section 3, essential metal printing materials. You see, you can't just print with any random metal off the street. You need specific alloys tailored for extreme environments. The big players include grade 5 titanium, that's T6Al4V, which is prized because it's incredibly strong but really lightweight. Then you have Inconel 718. This is a superalloy that maintains its massive strength even at 700 degrees Celsius, which is why it's the standard for turbine blades. We've also got aluminum for heat exchangers, stainless steels like 316L for structural elements, plus cobalt chrome and copper alloys. Each and every one of these materials is chosen based on a strict mission profile, dictating its needed strength, weight, corrosion resistance, and operating temp. So, the crucial point here is understanding the difference in how these metals are sometimes delivered, especially when we talk about filament for desktop printers, because there is a lot of industry confusion here. Composite metal filament is really just 5 to 60% metal mixed into plastic. It's cheap, around $25 to $45 a kilo, but it's purely decorative. It behaves just like plastic. Sinterable metal filament, on the other hand, packs 80 to 95% metal by weight. Yes, it's way more expensive, and yes, it requires a high-temperature kiln to burn away the plastic binder. But the result? You get solid, functional metal parts that reach 96 to 99% of true metallic density. That's a game changer. Which brings us to Section 4, the additive manufacturing advantage. Why do engineers actively choose this highly complex, high-heat method over the traditional casting or machining they've used for decades? The secret is in the geometry. Additive manufacturing unlocks what's called topology optimization. Basically, engineers use software to mathematically strip away material from non-load-bearing areas. This creates these incredibly organic, almost bone-like structures filled with internal honeycomb lattices. You keep the exact same structural integrity, but you reduce the part's weight by a staggering 40 to 60%. And the benefits go way beyond just making things later. Think about part consolidation. You can take a complex assembly that used to require 20 separate pieces all welded together, and you just print it as one single continuous object. For fluid manifolds, this completely eliminates leak paths. Plus, you can print complex internal cooling channels that weave through a part kind of like blood vessels. Traditional CNC machining physically cannot do that because you simply can't reach a cutting tool inside a closed metal box. Section 5, limitations and true costs. Because, honestly, it's not all magic. Physics and economics always demand a trade-off, right? We have to debunk the myth that 3D printing is always cheaper or easier. When you look at the cost breakdown, figuring out whether CNC or 3D printing wins is never a simple guess. It depends entirely on volume, geometry, and material. For simple, blocky parts and aluminum, CNC machining is almost always cheaper once you cross a tiny threshold of just 10 to 25 units. But if you're dealing with a highly complex titanium part with internal channels, metal 3D printing wins out, and that break-even point can stretch all the way up to 200 units. You can literally only find these true cost crossovers by running actual CAD data. And there are very real physical limitations to keep in mind, too. The equipment itself and those virgin metal powders are incredibly expensive. And parts don't just pop out ready to use. Extensive, labor-intensive post-processing is almost always required. From a design standpoint, your structural walls have to be thicker than 0.5 millimeters just to survive the thermal deformation of the laser. Any overhangs angled under 45 degrees, they're going to need printed support structures to keep them from sagging. And since the part is built layer by layer, engineers have to deal with micro-level realities like anisotropy, which basically means the part might be stronger in one direction than another, not to mention the risk of subsurface porosity from unmelted powder. Finally, Section 6, Real-World Industrial Applications. Despite those challenges, this technology is undeniably revolutionary, and this brilliantly illustrates the stakes. We're looking at the airframe of the F-22 Raptor and the IAE V2500 gas turbine engine, titanium and Inconel components, specifically optimized for weight and thermodynamics using additive manufacturing, are heavily integrated right into these systems. Whether we're talking about complex engine brackets or turbine blades, these printed metals are quite literally critical for flight safety and extending mission range. But it's not just up in the sky, it's also going inside the human body. Medical implants rely heavily on 3D printed 316L stainless steel for things like bone replacements and even orthodontic brackets. Now this is fascinating. Research shows that if the precise laser scanning speed isn't absolutely perfect during printing, microscopic crevices and pores can form in the metal. In the highly corrosive environment of the human body, like when exposed to artificial saliva, these tiny pre-existing pores can actually accelerate corrosion, expanding to several times their original size. So quality control down to the micrometer is absolutely paramount here. Metal 3D printing is truly transforming manufacturing. It's enabling us to build stronger, lighter, and vastly more complex parts that conventional methods simply cannot touch. So I want to leave you with this final thought. As this technology completely transitions from specialized rapid prototyping into full-scale mass production, how will the ability to print complex, aerospace-grade alloys on demand reshape the global supply chains that you interact with every single day? It is a pretty wild future to think about. Thank you so much for joining me for this explainer, and keep learning.
If you enjoyed this video, don't forget to like, subscribe, and turn on the notification bell so you never miss our latest engineering explainers. Thanks for watching, and I'll see you in the next video.